Good evening. So today we'll see properties of quantitative language and DCFLs. Okay. So take properties of DCFL, deterministic quantitative language, and quantitative languages. Deterministic quantitative languages are not closed under union, intersection, concatenation, set difference, quotient, cleans closure, positive closure, reversal, homomorphism. Okay. So why they are not closed? Example: a power n b power n union a power n b power 2n. Individually this is DCFL, this is also DCFL individually. But if I take union, already we have seen, so L1 is DCFL, L2 is DCFL, then L in union is not DCFL. You understand? Okay. Now this is the reason. So DCFLs are not closed under union, means if L2 languages are DCFL, L1 and L2 DCFL, their union may or may not be. Okay. So generally union, so if you take different languages it can be, but see when this is in this case, so it is not always, it is DCFL, then only we say union is closed. Sometimes not, sometimes yes, we say not closed. Okay. Now next, intersection is not closed. Example: a power n b power n c power n. You take union, intersection a power n b power n c power m. You take this one, it's a here m comma n whether greater than or equal to 0 or greater than 0, anything. Here this is DCFL because just skip the a's when b comes push, when c comes pop. Here push a when b comes pop, skip the c's. This is DCFL. Then what is the intersection? Here a's, b's and c's must be equal. A's can be any number. Here a's and b's must be equal, c's must be any number. So what is the intersection? Intersection will be a power a, b power a, c power a, which is even not a CFL. Okay na? So intersection is not closed, union is not closed. Okay. Got it? Next, concatenation. Suppose a plus b whole star is a regular language. Every regular language is also DCFL. Every regular is also DCFL. So I'll tell you at the end Chomsky hierarchy. When I say Chomsky hierarchy, you will understand. It is regular and also DCFL, and this is DCFL. So regular is DCFL and DCFL. So here you have to skip this. When A comes, you just push it. Example: a string is like this. Is this valid, invalid? Yes, of course. This is a power n b power n, it comes under a plus b whole star. Skip karo, skip karo, skip karo. A skip karke ye pop push karo. So this a you have to skip, this a you have to push. So how do you know? How do you know that? How the PDA will know this? So it has to go for NPDA. So that is the reason. This is DCFL. Concatenation is not DCFL. So not closed under union, intersection, not closed under union, intersection, concatenation. Okay now? Next, set difference. Are you following? Next, I'll go for set difference. What is set difference? L1 minus L2. L1 minus L2. What is L1 minus L2? L1 minus L2. This is L1 intersection L2 bar. So L1 is DCFL. We will talk about the L2 bar later. And if it is, even though this is DCFL, intersection is not closed. So that is the reason set difference is not closed. Next. So similarly, quotient is also not closed. Cleans closure is also not closed because L star again it gives you, what is L star gives you? L star gives you the union L power 0, L power 1, L power 1, union L power 2, L that is L square L cube. So union is not closed, na? So that is positive not closed. Reverse is also not closed. Reversal Y is not closed. Then so even though example this, if you reverse, it is not possible. So that is not closed, and a homomorphism also not closed. So you need not to go for this, just only answer how to remember. See, the DCFLs are closed under only two operations, that is complement, inverse homomorphism. So easy. The rest all are not closed. Okay, na? So DCFLs are not closed under. Yeah, I'm giving. Not closed under this one. DCFLs are closed under. DCFLs are closed under only two. DCFLs are closed under only two operations, that is complement and inverse homomorphism. Okay. So copy this one. DCFLs are not closed. Okay. Suppose example C, A power m B power n, A power n B power m C power n. This is DCFL. Okay. Yeah. This is, I'll tell you the best example. A power n B power okay, WCW transpose. Example, there is a language like this, the WCW transpose. Then W suppose A plus B whole star. W is A plus B whole star. Okay. This is DCFL. Is DCFL. Okay. Now, what I do here, I represent H of A as 0 and H of B is 1. and h of c I will go for epsilon. H of a is 0, h of b is 1, h of c is epsilon. Then w will be h of a is 0, h of b is 0, okay, a plus b whole star. Then c place epsilon, then w transpose. What will you get here? Here. So example, so w is any combination a and b, na? A plus b whole star. A plus b whole star means 0 plus 1 whole star. It's reverse. Okay. Then w, c place, in c place, I am substituting epsilon. So then what will be this? This will be w transpose. W transpose is what? It is CFL, but not DCFL. Okay. So homomorphism not closed under. Sorry, DCFLs are not closed under homomorphism. Okay. Now, so you can copy this. So not closed union. Are you copying? Not closed under. Okay, chalo. Now we'll go for next one. DCFLs are closed under union with regular, intersection with regular, okay, I do one thing. One second, guys. DCFLs, I have not taken the heading. DCFLs are closed under, I already told you only two operations. One is complement and inverse homomorphism. DCFLs are closed under complement and inverse homomorphism, and also these all languages are closed under next properties: union with regular, intersection with regular, set difference with regular. So guys, all languages are closed under these two operations, these three. Here, all languages are closed under these. All languages are closed. Okay. So DCFLs are, you just remember, they are closed under only two operations. They are complement and inverse homomorphism. Of course, these are closed. You need not to remember because every language is closed. That is the reason. Specially, you need not to remember. Union with regular, intersection with regular, set difference with regular. Okay. So, if L is DCFL, L complement is also DCFL. Okay. Complement closed. So, what is union with regular? Example, L1 is DCFL and L2 is regular. L2 is regular implies L1 union L2, L1 intersection L2, L1 minus L2 or L2 minus L1, L2 minus L1, all are DCFLs. Okay. If one is DCFL, the other is regular. So, union with regular, intersection with regular, set difference L1 minus L2, DCFL minus regular or regular minus DCFL. All are DCFLs. Okay. So, take this one. Regdipal, these, I think you have not attended yesterday's class, na? So this is these are the, so this is one, okay? This is complete. Heading is this one, properties of DCFL and DCFL. DCFLs are not closed under this one page, one slide. Then DCFLs are closed under these 5 operations. Means actually all are closed under here. All are closed. So only you have to remember this complement and inverse homomorphism. Okay, next. So guys, you copy this one also. Okay, so done. Next. Context-free languages are closed under union, concatenation, cleans closure, similarly positive closure. Whenever cleans closure comes, positive closure also comes, even in the top also. Okay, positive closure. union, concatenation, cleans closure, positive closure. So intersection is not closed, complement is not closed, set difference is not closed, quotient, reversal, homomorphism, inverse homomorphism, next prefix, suffix. Are you copying? So copy this, guys. Okay, so prefix and suffix, then cycle, and similarly union with regular, intersection with regular, then set difference with regular, Okay, copy this, copied. Okay, Rikiti. Okay, how was your exams? Completed or still going? Your exams completed or still going? Okay, good. Now guys, listen. So CFLs are closed under union, concatenation, cleans closure, positive closure. See, okay, the difference here, contest DCFLs are closed under complement, but CFLs are not closed. I have not written. Okay, so these properties you have to remember, guys. Okay, so one here I'll tell you. Listen, union with regular means these two. Let L1 is CFL. I do one thing. Let me give the not closed under that. Then you will understand. CFLs are closed under. Now I'll give you what are not closed. Where it is not closed. CFLs are not closed under not closed under intersection then complement set difference minimum maximum of then subset superset. So copy this. Okay, got it? Next, I told you no language is closed under infinite union, infinite subtraction, infinite set difference. That also you can add. Okay, copied. Next, alt infinite union, infinite subtraction, infinite intersection, infinite set difference. Okay, copy. Infinite set difference means here take L1 minus L2, L1 minus L2 minus L3 minus so on, L1 intersection L2 bar, intersection L3 bar, so on. CFLs are not closed under complement, one thing, okay, and one more, not closed under intersection. Abhijit, CFLs are not closed under complement, one thing, and not even closed L1 intersection L2. Suppose L2 bar is also DCFL, but intersection not closed, na? So that's it. Okay. Next guys, and we'll go for union with regular, intersection with regular, set difference with regular. Okay, this is about CFL. CFLs are closed under. So this is okay. One important thing, please concentrate here. CFLs are not closed under intersection, complement, set difference. Mainly you remember these points, and no doubt, and subset, superset, no language closed. Subset, superset, no language closed. No language closed. Here also no language closed. Okay. Subset, superset, infinite union, infinite intersection, infinite subset difference. No language is closed. That same I have given you. I told you in the properties of regular language also. Okay, na? And alt, of course, alt it is closed, regular language closed, but no language closed under these 5 operations. Now come back. So remember, if L is cont is free, it's L complement of L, may or may not be. But L is DCFL, its complement is also DCFL. Okay, only difference. L is CFL, complement may or may not be. If L is DCFL, complement is also DCFL. Okay, now look at this guys. Intersection with regular, union with regular. What does it means? If L1 is CFL and L2 is regular, implies, look at this, L1 union L2, L1 intersection L2, L1 minus L2 are also CFL. Okay, na? Listen carefully. What is L1 minus L2? L1 minus L2. Listen, guys. Are you following? L1 minus L2. What is L1? L1 is, I write here. What is L1 minus L2? L1 minus L2. I am writing L1 minus L2. What is L1 minus L2? L1 intersection L2 bar. What is L1? CFL. CFL intersection, what is L2? Regular. Regular complement. CFL intersection regular complement is also regular. CFL intersection regular is CFL. Okay, na? Then, okay, now look at these guys. Now I'll go for, because intersection of regular and CFL, intersection CFL and regular, or union and CFL, union CFL, or CFL intersection regular is also CFL. So CFL intersection regular is CFL. Now L2 minus L1. Look at this carefully. L2 minus L1. What is L2? L2 is regular, na? L2 is regular. Oh, one second, guys. L2 minus L1. What is L2 minus L1? L2 intersection L1 bar. First of all, we must see what is L2 minus L1. L2 intersection L1 bar. Okay, L2 intersection L1 bar. What is L2? L2 is regular. We have taken L2 as regular. L2 intersection L2 intersection L1. What is L1? CFL. L1 is CFL. L1 is CFL. Okay. L1 CFL complement. Context free languages are not closed under complement. Not closed under complement means the complement of a context free language may be context free, may not be context free. No guarantee. So in this case, we will upgrade this language. Upgrade means what is the next level of first regular, after that DCFL, after that CFL, after that CSL. Don't worry, everything you can understand your own. You can write your own this Chomsky hierarchy. We will see at the end of the Turing machine. So CFL are not closed under CSL. So sorry, CFL are not closed under complement. CFLs are not closed under complement. So that is the reason we will upgrade this language. So CFL next level is CSL, and CSL are closed under complement. Regular intersection CSL. So regular with union with regular, intersection with regular, certain difference with regular is always any language closed. So CSL. Are you following? See guys, here one is CFL, the other one is regular. Then L1 minus L2 is CFL, whereas L2 minus L1 is CSL. But not CFL. So you must be very carefully. So set difference with that is union with regular, intersection with regular, set difference with regular, set difference with regular. Are you doing regular minus CFL or CFL minus regular? CFL minus regular is CFL minus regular. CFL minus regular is CFL, but regular minus CFL is not CFL. Okay, so copy this guys. So have you copied this not closed? Have you copied this not closed? Okay, not closed. This is closed. This is closed. Copy na? This is closed. Now take these examples. Take these examples, guys. It means they take this one. Okay, now, so what is left linear? Somebody is asking the doubts. Left linear grammar. In the types of grammar I have told you, left linear grammar, the right side leftmost symbol either is AW or W. No, sorry, either is BW or W. Okay, here the first symbol on the left hand side of the arrow, the first symbol on the left side of the arrow must be a non-terminal and followed by only terminals, and it can be only terminal. Okay, so only terminal string. Okay, or if non-terminal is there, it must be first symbol. If on the right hand side, if non-terminal is there, it must be first symbol, that too only one symbol, and followed by terminal string or only terminal string. Here A and B are non-terminals and W is a terminal string. And what is left recursion? Left linear and left recursion are different. At the same time, right linear. Right linear, what is right linear? The rightmost side of this, right hand side of rightmost symbol, rightmost end of the right side, that is either is WB or W. Whereas left recursion actually we have not done. We will do in the compiler design. We will do this part, left recursion. So left recursion is right side first symbol must be same as the left side of the arrow. This symbol and this symbol must be same. And here alpha is what? Alpha can be any combination. There can be more A's also, more B's also, any number of non-terminals and terminals. Here alpha A is a non-terminal. Alpha can be any combination of terminals and non-terminals. We will see in depth when we go for comparison. So just leave the questions on ambiguity and left recursion, left factor. All these questions you can leave because we will do in compiler design left recursion. But this is left linear. Clear? So that's all, guys. We have done the push down automata. We will go for Turing machine. We'll go for Turing machine. Okay. Any doubt? So this is left linear, already we have done. Left recursion need not to copy. You need not to copy, guys. We will do in compiler design. That's all. Chale? We'll go to Turing machine. This is a new topic. Okay, Turing machine. चले. So Turing machine, actually it is used to accept, one second, guys, Turing machine, whatever computer can do, Turing machine also can do. Whatever computer can do, Turing machine also can do. Okay. Are you following? Whatever computer can do, a Turing machine can do. That means if you can write a logic, for any problem, to implement that logic, there exists a Turing machine. Okay? Simply Turing machine is equal to computer. Whatever you can do with the computer, Turing machine can do the same. So actually, Alan Turing has invented this Turing machine in 1936. Alan Turing has invented Turing machine in 1936. Okay. So here the Turing machine mainly used for accepting recursively enumerable languages. So in this topic, what is Turing machine, how to represent Turing machine, how it can accept the strings, then design part, then what are the different types of Turing machine, then we will go for universal Turing machine, Church's Turing thesis, then recursively enumerable language and their properties. After that, we will go for Chomsky hierarchy. Then at the end, I will give you a table which gives you all properties between all these languages. Properties among all the language, regular, CFL, DCFL, CSL, recursive, enumerable, all properties I will give you as a one table. Okay, na? So with that, Turing machine will be completed. Then we will go for last topic, undecidability. So most probably I am expecting by Sunday at any cost will be completed. Sunday. Okay. So I take Saturday long hours. It's maybe 2 o'clock or 3 o'clock. I'll start 2 to 10 or 3 to 10. Okay. Now, so take Turing machine notes. Take the notes. Whatever a computer can do, the Turing machine also can do. Okay. Full stop. I repeat, whatever computer can do, Turing machine also can do. Continue. Whatever can be done with logic, whatever can be done with logic, Turing machine can do. Okay. Next. Turing machine is used to accept. Turing machine is used to accept recursively enumerable language is used to accept recursively enumerable language. Saturday morning not possible, Rakati. It is not possible on Saturday because I have offline class. Okay. Now, listen guys. Guys, Turing machine has a tape of infinite length. Turing machine has a tape of infinite length, which is divided into number of cells. It is divided into number of cells. Each can store only one symbol at a time. Turing machine has a tape of infinite length. This side is infinite, this side is infinite. It has a tape of infinite length divided into number of cells, and each cell can store only one symbol at a time. One symbol at a time. Okay. It has a tape of infinite length divided into number of cells. Each cell can store only one symbol. In a cell you cannot place two symbols. And this is connected to a finite control mechanism through a read or write head. So this is connected to this finite control mechanism through a read or write head. So in the case of finite automata and Turing machine, there will be only read only head. There will be read only head. But in the case of Turing machine, it is read and write head. Means it can read and it can replace that symbol with another symbol. Read and write head. And it will be in some state every time. The automata will be in some state. Okay. And this is the input string, and before and after these are the blanks. All these are blanks. Here this is an input string A B B. Okay. Now this tape is connected to finite control mechanism through read or write head, which can move either one cell left or one cell right only. That means after finishing this transaction, the machine can come to this cell or the machine can come to this cell. Okay na? After completion of this transaction, the machine can come to this cell or the machine come to this cell, either here or here. That's it. Only one cell, not more than two cells. I repeat, Turing machine, it is very easy topic guys. The Turing machine has a tape of infinite length. It is divided into number of cells and each cell can store only one symbol. This is connected to a finite control mechanism through read or write head. This head can move either one cell left or one cell right. This head can read and also write. Okay. Now in every transaction, the Turing machine takes the present state and present symbol in the cell from the tape under read or write head. Means wherever head is indicating, in that place, in that cell, whatever input symbol is there, that symbol, whatever symbol is there, that symbol from the cell will be taken. in every transaction that Turing machine takes the present symbol in the cell from the tape under read or write head to give the following. What? So here after completion of this transaction, as usual, what is the next state? Maybe same, maybe different. And after completion of this input symbol is what symbol to be replaced? With what symbol? A. Shall it be A will be A only, or A will be replaced by some other symbol? Okay. What is the next state? That will be decided. To what symbol the present symbol is to be replaced? If I write A will be A only. If I write X will be A will be replaced by X. And the direction, if I write L, the head comes to here. If I write R, the head comes to this cell. So after completion of each transaction, first of all, it takes the present state and in symbol in the cell under the read or write head. Okay, in the cell from the tape under the read or write head to give the following. What it gives? It gives what is the next state, to what symbol this symbol is to be replaced, and what is the direction these will be. Okay now? So now take this. In every transaction, copy. Better you just copy this this one, then I will give you will understand better. Copy this diagram. Okay. Now take this one. In every transaction, the Turing machine takes the present state and present symbol in the cell from the tape under the read or write head Under the read or write head, this is head. Under the read or write head, to give the following. To give the following. As usual, what? Next, what is the next state? What is the next state? What symbol, the present symbol is to be replaced, and what is the direction? Okay, na? What is the next state? To what symbol the present symbol is to be replaced? The present symbol is to be replaced. To what symbol the present symbol is to be replaced? And the direction. The direction of the read or write head. The direction of the read or write head. Okay, na? I told you what is the next state, to what symbol to be replaced, and what is the direction, left or right. Okay, na? Next. Suppose, guys, if I define what is the next state, what symbol to be replaced, and direction. If I don't define, example empty, then what? The machine stops. The machine stops. If you don't define, the machine stops. So that is what. If you define, these three will be happen. If you have not defined, then it will stops. Whether to stop or not. Whether to stop or not means if you have not defined, the machine stops. If you have defined, the first three will be performed. Okay? Copy. Next, we will see the structure. Turing machine is a 7-tuple. Turing machine is a 7-tuple. So generally we represent with the M, stands for machine. Q, sigma, tau, delta, Q naught, blank, F. This is the 7-tuple. Okay, now. So as usual, what is Q? Finite, non-empty, finite non-empty set of states. Finite non-empty set of states. This is finite set of inputs. finite set of inputs, finite non-empty set of states, finite set of inputs. Guys, this is whatever symbols we use in the tape, they are called as tape symbols. I repeat, whatever symbols we use in the tape, they are called as tape symbols. So all the tape symbols will be in the tau. It is finite set of tape symbols. Finite set of tape symbols. Okay. Now one more thing. Whatever the symbols in the sigma, also will be in tau. So sigma is proper subset of tau. Every symbol in the sigma also be in tau. Okay. Now this is transition function. This is transition function. So generally the trans function we have seen already. It takes the state and symbol from the and symbol from the tape. That symbol can be a input symbol or tape symbol. I repeat, it takes the state from Q and symbol from the tape. What that symbol? It can be a input symbol, it can be another symbol. So tape symbol. Of course, every input symbol also tape symbol. Every input symbol is also tape symbol. So that is the reason I say Q cross tau into what it will give. What is the next state and to what symbol the present symbol replaced and the direction left or right. This is the actually you remember. So the previous one what I gave. So there what did I give? Here I gave like this: delta of Q naught comma A equal to Q1 comma X comma suppose left or right. Okay. If I write left, it goes to. Okay. Now this is what Q naught and Q dash, Q naught and Q1 are the states. This is the state. This is also state. And what is A? A is a input symbol. Not only input symbol, it can be a tape symbol. And every input symbol also tape symbol. Okay. And this one X is what? Also tape symbol. So that is the reason we write A and tau into tau. So A comma X both are belongs to tau. Every input symbol is also tape symbol. So this is the mapping. Q cross tau. It takes a state and symbol from the tape. Gives what is the next state, what is the next symbol, what is the direction. Okay na? So Q cross tau into Q cross tau cross direction. And you know very well, this is initial state. Every automata must have starting state. Initial state. And initial state is the one of the state from set Q, and this is a special symbol called blank. It is a special symbol called blank. Okay, this is not necessary, I am dating. Special symbol called blank. A blank is a part of tape symbols. Blank is not a input symbol. Blank is not a input symbol. Blank is a tape symbol. Blank is a tape symbol, not a input symbol. And in some textbooks or some website, they will use the instead of blank, instead of this, they may use this symbol, or they may use this symbol. Different others, different they uses different way. Okay na? So I will use this. Sir, then how to indicate, how to identify in the gate examination if the question is given? Don't worry, they will mention what is what. Okay na? So even though they don't mention, you will have this na. Already I am saying this is blank generally, or this is blank, or this is blank. But I use this separation. Okay na? Next. So this is the blank, and blank is a tape symbol, but blank is not a input symbol. Next, as usual, you know very well, this is set of final states. Set of final states. Set of final states. F subset are equal to Q. F subset are equal to Q. Set of final states F subset are equal to Q. Okay, so copy this, guys. I will short it down. Okay, so is this clear? Now Turing machine is at 7 tuple. Copy. Okay, next. Q cross tau into Q cross tau. Okay, done. Now guys, we will go for the how to represent a Turing machine, and before that we will go for ID. So now we will go for ID, instantaneous description, then initial ID, then representation of Turing machine. These are the topics, and one more thing, acceptance by Turing machine. 3 topics: what is ID, what is initial ID, what is how to accept the strings, then representation of Turing machine. Then we will go for the design. So this is a design. Until design part is a easy topic and it's not a lengthy topic, but the major important thing is here this recursive and recursive enable. Okay. Okay. Now take instantaneous description. Instantaneous description. From this topic you will get the questions from recursive and recursive enable, and design part also they can ask you the questions. And most important in this, after this, is undesirability. Undesirability, every year they used to give the one question. Okay. Instantaneous description. What is NID? Simple, guys. I'll go for the previous one only. Why should I go for again wasting the time? So guys, how to represent the present situation using the ID. Okay na? So here this is read or write head. This is read or write head. Okay. Now what is the present state of the machine? Q0. What is the present input string? A is the present input string. So we write this present situation like this. Okay. We represent the situation like this. So this is the A B double A double B. A B double A double B. A B double A double B is the input string. And the present input symbol is A, this one. The present symbol is this one. Okay, this one. And what is the present state? Q0. Q0 is the present state. This is the way of representing the situation using ID. A B double A double B. A B double A double B. And okay, the present input symbol is A. And before and after you can write the blanks. You can ignore the blanks or you can write the blanks. This is the one way. You can write any number of blanks. Left side any number of blanks and right side any number of blanks. But when we are representing the using ID, one blank is enough. And even you don't write the blanks, then also no problem. Or or the same you can represent like this also. Or look at this, guys. Here what is the input string? A B double A double B. What is the present state? Q0. What is the present input symbol? A. So look at this. A B. We write the present state. Q0 before this present input symbol. So what does it means here? Q0 is the present state and A is the present input symbol, and these are the remaining input symbols. So before this A B is there. Okay. After this A double B is there. Okay. And before and after you can go for any number of blanks. See, I have clearly I wrote. So Q0 is the present state and A is the present input symbol, and before and after the remaining input string. And you can ignore the blanks or you can write the blanks or you can ignore the blanks. Okay now? So this is the way of representing the present situation. You just copy this one, and this is called an ID. So okay, ID. Okay. Abhijit, you are blank. If you have any problem, please rectify this one. So earlier also you have done some. Yeah, okay. Okay, I'll tell you. Abhijit, Manoj, here, this is the present input state. What is the input string here? A, B, A, B. What is the present state? Q naught is the present state. What is the present input symbol? A is the present input symbol. So, this is the present input symbol and this is the present state. Okay. This way, or you can represent like this also. The present state and present input symbol. This is the present state and present input symbol. Before AB is there and after A is there. This is the one way of representing. Okay, na? Now, initial ID. Initial ID. What is initial ID? Next, take the heading. Initial ID. Next, initial ID. Initial ID. If M equal to Q sigma tau delta Q naught blank F is a Turing machine, then the initial ID is okay. Guys, look at this one. The initial ID matlab, suppose a given input string is given, okay, that can be anything. So whenever machine starts, it starts from the leftmost symbol of the input string. I repeat, whenever the machine starts, it starts from the first symbol of the input string. It starts scanning from the leftmost symbol here. Whenever the machine starts, it starts from the initial state Q naught. So whatever the initial state, Q naught is the initial generally. So this is the initial position. How do we represent? We write the present state Q naught before this present input symbol, and this is the remaining input string is B, A, B, and before and after you can use any number of blanks. Guys, tell me, what is this whole? This is the input string, na? So Q naught. This whole is input string. Generally, W is the input string, and before and after the blanks. Do you understand? Okay, guys, do you understand? So this is the input string. This whole is input string. So I have taken as W, and Q naught is the initial state, and before and after blank, after that any number of blanks. So this is the initial position. That initial position we can represent like this. So here, if M equal to this one, then initial ID is Q naught W, and before and after you can write any number of blanks, or you can ignore the blanks. Even though you can ignore, no problem. Okay. So this is where what is Q naught? What is W? What is W? Is a terminal string. Okay, na? So it is input string. And Q naught already I have given. By giving like this, what you must understand? Q naught is the initial state, and blank, these are the blanks. What is W? Combination of input symbols. Okay, so take this one. Okay. Yeah, actually W is sigma star only, because not tau star. W is not tau star. No, no, because W is always input symbols. The input string is always combination of input symbols. You cannot write as W as tau star. Okay na? After Bansari. Diagram. Okay. So anyway, this is not correct. So this is the initial ID, guys, and take this diagram. Okay. Now, guys, acceptance by Turing machine. Next. So we have seen what is in ID, what is initial ID. Now acceptance by Turing machine. Acceptance by Turing machine. So how do you say that a string is accepted by finite automata? A string is accepted by finite automata if it starts at initial state and the total string, if it is scanned, and if it stops in a final state, then the string is said to be accepted. Whereas in the case of push down automata, we start from initial ID. In the case of finite automata, we start from initial state and it must stop in final, string must be scanned completely. In the case of push down automata also, it must start from initial ID. After one or more transactions, it must reach either final state or string empty, either final state and string empty, string must be empty, or any state, string empty, stack empty. So in both cases, string must be empty and either final state or empty stack. Here also string must be empty. Empty matlab string must be scanned completely. Here also string must be scanned completely. Okay. Now, so you remember na? In the case of finite automata, it has to start from initial state and must stop in a final state. And string must be scanned completely. In the case of PD also, it must start from initial ID, whereas here initial state, initial ID. And in both cases, string must be scanned completely. Okay guys, now listen. Acceptance by Turing machine. Here also, you must start from the initial ID. What is the initial ID? Q not W. After one or more transactions, now listen, suppose this is the initial ID. Listen carefully. Initial ID. After this transaction, suppose Q0 is replaced by Q1. Okay. Q0 is replaced by Q1 means not replaced. Sorry guys. The state is changed to Q0 to Q1. State is changed to from Q0 to Q1. Let this input symbol is replaced by X. Okay now. Let this head has moved to right side. Are you following? Earlier it was in Q0. After completion of this transaction, let the machines changes to the state Q1 and let A is replaced by X. Let the head is moved to right side. Okay now. Then after this again, let Q1 will be Q1 will be Q1 only. Let B will be B1 only, and let head moves right side. Suppose example right side. Okay, so it can go to left side, it can go to right side, because as per the transactions definition, it can go to where is the definition here? It can go to either left side, or right side. Say, okay, let's listen, guys. Even though you don't understand, just it is very simple concept. Listen. So after this particular transaction, now the machine is in Q1. Input symbol is A. Let after this, let the machine goes to Q2. Let A will be replaced by Y. Example. Let the head moves left side. Let the head moves left side. So after every transaction, the head can move right side, or always right side, or always left side, or sometimes left side, sometimes right side, sometimes left side, sometimes right side, sometimes left side, always right side, always left side. It can move anyway. Depends on your requirement. You will design. So sometimes we will see the designs also. Okay na? Sometimes we must move always right side only. That design we will do. And sometimes we move right side, again left side, again right side, again left side. We can do the design like that also. So here only two conditions must be satisfied. If the string is accepted, two conditions must be satisfied. What are they? It must start from the initial ID. Okay. After that, when the machine stops, it can stop anywhere. Either first symbol or here. It can stop anywhere. Where the machine has stopped, it doesn't matter. So the thing is, two conditions must be satisfied. One is it has to start from initial ID. After that, wherever machine stops, it has to stop in final. That's it. It has to start from initial ID. When the machine stops, it must stop in a final state. Suppose the machine has stopped here. In the case of Turing machine, it is not necessary to check whether a string is scanned completely or not. Okay. In the case of finite automata, even though the machine has reached the final, if the string is not completed, not scanned completely, not accepted. In the case of push down automata, even though the machine has reached the final or the stack is empty, in both cases, if the string is not completed, we say not accepted. But in the case of Turing machine, we don't bother at all about the string. Whether the string is scanned completely or not completely, it doesn't matter. If the machine stops in the final, then the string is accepted. So it has to start from initial ID and it has to stop in a final. How do you represent this situation? Look at this, guys. Look at this. We write, okay, suppose let the machine has stopped here. Let the machine has stopped here. Here, how do you represent this one? We write xb and the present state qf before y. So y, qf is the present state and y is the present input symbol and the remaining input symbols. Okay na? Guys, what are these? These are the combinations of input and tape symbols. Simply you can say tape symbols. Let it be alpha 1 and these are the combination of some tape symbols alpha 2. I have not done. Suppose B can be replaced by some other symbol Z, or this is X, something like this. So here only thing is it has to start from initial ID. When the machine stops, it has to stop in a final state. It has to stop in a final state. Okay na? So where what is QF? It is a final state. And what are alpha 1 and alpha 2? Any combination of tape symbols. This is, guys, this is the acceptance by Turing machine. So by starting at initial ID, a string is said to be accepted. A string is said to be accepted. A string is said to be accepted by Turing machine if it starts at initial ID and terminates at some final state. That is Q naught comma W. So let the blanks. After one or more transactions, alpha 1 QF alpha 2, where what is QF is a final state, and what is alpha 1 and alpha 2, they are the combinations of tape symbols. Copy. Not necessary pumping lemma for CFLs. Okay, I'll tell you. Otherwise, not necessary pumping lemma for CFLs. Okay. Next, representation of Turing machine. Representation of Turing machine. Okay, representation of Turing machine. You can represent the Turing machine in two ways. One is by transition diagram. One is by transition diagram. The other one by transition table. By transition table. Transition table. Trans diagram and trans table. Okay. So we'll go for the diagram first. Guys, look at this one. By trans diagram. So copy this one. Representation of Turing machine. I'll delete this. Okay, now we see the transition diagram. Guys, look at this. You just try to understand the meaning of the move. The meaning of the move. Okay. Q0, Q1, here Q0, Q1, Q2 are the states, okay, and A comes X replaced by R. Just I will explain. Just look at this one. So what is the meaning of this? So don't ask me. Actually, even I don't know what is the meaning of this one, because intentionally I am not writing anything. I want to explain what is the meaning of the move. Okay, when we go for the design part, I will tell you how to design. So when to change the state, how to write the moves, all we will do. Okay, we will see. What is the meaning of this one? You just concentrate the meaning of this one. In Q0, if A comes, I repeat, in Q0, if A comes, or if the machine scans A, the A will be replaced by X. Suppose in the tape there is A, okay. A will be, after scanning this A will be replaced by X. Head moves right side and state goes to from Q0 to Q1. That is the meaning. Okay. Whereas in Q1 A comes, A will be A only. Suppose A will be A only. Are you following? And A will be A only. The head moves right side. The head moves right side. Okay. And state also same. Suppose in Q1, example, in Q1 if B comes, B will become Y. Example, Q1 B comes, B will become Y. Head moves left side, it can come back and state changes to Q1 to Q2. So that is the meaning. So you understand try to understand the meaning. In Q1, B comes in Q1, B comes, B will be replaced by Y, head moves left side. Sir, you wrote left side but you are going right side. Okay, this is the change of the state, boss. This is not the change of the direction. So from machine Q1 to it goes to Q2, but head moves left side. Similarly, when Q2 X comes, X will be X, and head moves right side, but state goes to Q0. That is the meaning. Okay na? So this is the way of representing the machine by transition diagram. Same you can represent using the table also by transition table. By transition table. Okay, this is by trans diagram. Okay, now you can copy this. How to represent using the table. Okay, what are the states here? Here the states are Q0, Q1, Q2, and initial state is Q0 and the final state is Q2. Okay na? The final state is Q2. And here what are the tape symbols? The tape symbols will be all blank, A, B, X, Y. All these are the tape symbols. Okay na? Now look at this, guys. In Q0, A comes. A will become X. And move right side. Go to Q1. Hello guys, I repeat. In Q0, A comes the same I am representing the table. In Q0, A comes, A will become X, move right side. Q0, A comes, A will become X, move right side and goes to Q1. Okay na? Now come to Q1. In Q1, A comes, A will be A. In Q1, A comes, A will be A. Move right side and state will be the same. In Q1, A comes, A will be A, move right side and same state. Now in Q1, B comes, B will become Y, head moves left side and goes to Q2. And here I have not defined for this all. You need not to define for every symbol here. In the case of Turing machine, in the case of PDA, you need not to define for every combination. Now in Q2, I have defined for A, but I have not defined for blank. In Q2, A comes, A will be A, head moves left side, same state. Okay na? Whereas in Q2, Y comes or X comes, in Q2, X comes, okay, X will be X, and move right side, go to Q0. Okay, now last one, see, in Q2 Y comes, Y will be Y, head moves left side, same state. So this is the way of representing the Turing machine using the table and using the diagram. Okay, that's all guys. Take the break, we'll come back. Okay, we'll continue after the break.